Hi, I'm Antonio Sala. In this video we are going to start a series of videos with the overall goal of understanding the meaning of the singular value decomposition of the static gain of a process to control. And in particular, there are some principal maneuvers that are intuitively related to, let's say, in a process like this, in which we have two resistors in red and two blowers blowing cold air in green and three thermocouples, well, we may think on actuator fusion, let's say, in which 1 and 2 are operated together because, increasing resistor power and decreasing blower intensity is kind of the same. Or we may decide to control the mean of the temperature readings, so these ideas of sensor fusion or actuator fusion may be interpreted in terms of the singular value decomposition. And so we'll start in this video with reviewing this basic theory outline on that SVD and associated SVD decoupling. Okay, we'll first start considering a scaled gain matrix in the sense that we'll assume that input ranges in the interval plus minus 1 and the desired output increment also range in the interval plus minus 1. Then we may carry out the singular value decomposition of that scale gain matrix. And once we have that scale gain matrix, we can identify the so-called output directions as the columns of U and input directions as the columns of V, and the principal gains in the diagonal of S. U and V are orthogonal matrices. Their inverse is equal to their transpose. So we may have this G2 matrix with 2 controlled outputs and 4 manipulated variables, 4 actuators. And if we carry out the singular value decomposition, we get this SVD in which we identify this principal maneuver 1 with this output direction, this input direction, and this principal gain, which means that when I apply the manipulated variable input in the first column of this V2 matrix, then I get an output in the direction of this column of U2, which is norm 1, but the output has norm 2.45. I can also identify second maneuver with this output input directions and this principal gain of 1.13. So that means that this norm 1 input produces an effect in the output direction, which is also norm 1 in the column of U2, multiplied this column by 1.135. This is the low gain principal maneuver in which the actuator has half the effect, let's say, than in the high gain maneuver. With suitable scaling, we consider we are able to control our process if the minimum gain is above 1, because we can reach the unit sphere in output with the unit sphere in input. In this case, unit circle, because we are with 2D output, and it will be the 4-dimensional hypersphere in input, because V2 is, composed of 4 perpendicular rows. The thing is that, okay, these 2 columns in here are the so-called null space, and actions in this direction should not be used for control because, well, it means some increment in my actuators that has no effect whatsoever in the outputs. And the intuition on that is sort of, if we go back here, let's say that imagine that I consider increasing the voltage to the resistor 1 and at the same time increasing the voltage to fan 2. Then the net effect with suitable gains, let's say, can be 0. The extra heating by the resistor is just blown away by the extra cooling of the fan. So that's the intuition behind what we consider a null space maneuver, and okay, we should not execute such null space maneuvers. So these are the principal maneuvers and its interpretation in a process. It's also important to acknowledge the relationship between SVD and least squares problems. Least squares problems are solved by pseudo-inverse matrices, and basically pseudo-inverse is computed from SVD by swapping the role of capital U and capital V, here we have them, and inverting S. Well, inverting only the non-zero diagonal values in S, asserting that SVD and pseudo-inverse least square problems are close cousins, and in fact the idea is that least squares problems amount to not using null space input maneuvers or not requesting null space output setpoint changes. We'll see some examples later on. Once we have this review on what principal maneuvers are, we'll now consider what is called singular value decomposition based decoupling, or SVD decoupling in short. What does this mean? Well, I have my gain matrix with suitable scalings, and I compute its singular value decomposition like this. And now we will imagine this change of variable. Well, there will be some observations in this change of variable we'll discuss later on, but because we'll actually implement the inverse change from U SVD to U, but we'll leave it for the moment being. And the thing is that, well, okay, if I just copy this change of variable here, now I will replace this equation in here, then I will replace this equation in here, and now I will realize that as U is an orthogonal matrix, transpose is inverse, then U transposed U ends being the identity matrix, so it disappears from my manipulations, and V transposed U is what we called USVT here. So if we make that sequence of changes of variables, the apparent behavior between these SVD related variables is the diagonal matrix S. And importantly, it is such even with non-square plans, with suitable dimensions of matrices U and V. So in the example we were discussing, let's say YSVD would be the projection of the two sensor readings onto each of the directions given by the columns of U2, and the USVD will be the projection of the input maneuvers in the directions given by each column of the V2 matrix. But okay, as these ones are in the null space, in fact what we call the economy size decomposition will consider only these two components in the change of variable to conform USVD. More on that later. The thing is that we get this apparent diagonal behavior, so the implementation of this is as follows. What we will do is, from my sensors, actual readings Y, I will compute YSVD with this U transposed stuff. Well, in fact, if we have a set point, then I will compute the error in principal maneuver coordinates by multiplying by U transposed. Then I will design a controller K of S that, okay, as from YSVD to USVD, the apparent process at low frequencies is a diagonal matrix, then it means that at low frequency for slow signals, the first component of SVD error seems decoupled from the second one, in the sense that only the first component of USVD seems to have effect on the first component of SVD error, and likewise with the second one. Hence, this is why it's called SVD decoupling, because I can design K of S as a diagonal controller. I'll have, say, a PID 1 for controlling principal maneuver 1, a PID 2 for controlling principal maneuver 2, and then some zeros. And okay, depending on if I am using the economy size decomposition or the full decomposition, I may have additional rows or columns of zeros so that matrix dimensions are set up in the right way. But okay, that's implementation detail. The thing is that okay, K of S is a diagonal controller, and once I have USVD, then I will not use this change variable as I warned you before, but I will actually use this one. I will transform from principal maneuver coordinates USVD to physical coordinates U by multiplying by matrix V. So even if this was, helpful for getting the idea on the change of variable, the one we are going to actually implement in our control design code will be this one. So this is the final SVD decoupled controller, in which I have a diagonal controller K in the middle of U transposed V. So U transposed and V are somehow in the place they will be in the pseudo inverse we mentioned earlier on, because okay, controlling is sort of inverting the plant to transform it in something else, my reference behavior. Well, the thing is that this SVD controller, then it will be what I would implement, but we need last refinement, in the sense that, okay, imagine that I have this matrix and I carry out this singular value decomposition and I get these things. Then, okay, we have a problem here because we have a principal gain here of 0.02. So if we wish to move the three outputs touching the unit sphere at any arbitrary point, then we will need 50-60 times more gain. And of course, that isn't likely to happen. But anyway, even if it happened, the issue is that if I multiply everything by 100, I would obtain 3 gains, all of them above 1, but the condition number will be 2.9 divided by this. It is 160, so it's simply unacceptable, in the sense that, okay, a 1% error in my input can translate in a worst-case situation to a 160% error in my output. Errors above 100% are unacceptable, so this will not work in practice in most settings, even if I had 100 times more power and I changed the scaling suitably. So the thing is that in here we have the theoretical null space with 0 gain, 0.000, but in here we will add this principal maneuver to the so-called practical null space, in the sense that trying to control this thing with very low gain will lead to saturation problems, and also as my model has, let's say, 100 times lower signal to noise ratio in identification experiments, my model will be also likely very bad. So bad model quality, low gain will give me saturation and risk of bad performance due to modeling errors. So we will decide not to control this thing, and we will have a two-dimensional practical null space. So we should control only these two high gain principal maneuvers, because instead of having a condition number of 160 and needing 100 times more power, in here I have a perfectly good power to control these two maneuvers and a condition number of 2.5, let's say. 2.9 divided by 1.1. But the thing is that I will move my 3 controlled outputs only in this 2-dimensional subspace spanned by these 2 columns. If I do that, it will work. If I try something else in this other direction, then I will fail miserably. So I decide to control 2 maneuvers. And then, instead of this, the only thing I will implement is using the first 2 columns, in this case Q as 2 columns of capital U in the formula, and the first 2 columns of V in this formula to get the actual physical control action. So once I incorporate also some scalings, this will end up in this block diagram. The scaled variables have size 1, and then I must multiply scaled variables by some scaling matrix EU to get physical U, or I must divide physical variables E, divide by the EY scaling to get scaled error. Then after scaling, I do the SVD transformation, my diagonal controller, and all of this will be my SVD decoupling based controller. And well, this thing here is the so-called realizable reference, because SVD will be related to some least squares fit, and my SVD controller will have 0 error, not when this reference is achieved, but when some projection on the principal output maneuver subspace is achieved. So this is how to compute it, but for brevity, we'll leave that discussion out for SQL materials. So for the moment being, we end the video here. Summarizing, we have explained what the principal maneuvers are, the relationship of SVD with pseudo-inverse and least squares problems, and we have explained the intuition behind this SVD decoupling block diagram via some principal maneuver change of variable. In forthcoming videos, we'll see a handful of examples in detail to better grasp the intuition on all these matrices. So we end the video here. Thanks for watching.